So, hello everyone. My name is Anastasia. I'm a coordinator of the Treeserach Research Infrastructure, and today I have a great pleasure to invite Nicholas Martin from the Ansys company. And Nicholas is the Academic Development Manager. Today he will present to you the capabilities of the very unique Ansys Granta software. And this software can be used for multiple applications, both for the research and for the education. And it's also a very useful tool for the industry. And with this software, you can do advanced data post-processing, analytics, the data informatics, and then also the visual presentation of your data. So please, Nicholas, it's a great pleasure for me. The floor is yours.
All right, thank you, Anastasia, and good afternoon, everyone. I'm very pleased to have the opportunity to give this session and run this session today. As mentioned, my name is Nicholas. I have a background in material science. This is the area where I did a PhD on composite materials. And just to contextualize a little bit where all of this comes from, I joined after my PhD a company that was called Granta Design at the time, based in Cambridge. Where I was working in supporting teaching with a software tool called Granta EduPack. Some of you on the line might be familiar with this because it's an educational tool that is quite commonly used in Sweden universities. Granta Design got acquired in 2019 by Ansys and is now more embedded into the wider simulation ecosystem. And actually, the purpose of my talk today is, as part of the title states here, is to talk about data-driven science engineering and materials informatics using some of our platform tools. So to actually cover this, this is the agenda that I will go through. First, I'll set a bit the scene and talk about materials data digitalization. And especially how that affects the research and materials research space. So talking about the what, the why, the how, and the who. And then I will say much more about our data-driven science engineering platforms that really looks into supporting materials-related research in a collaborative environment. And I'll end by saying a few example of industry and research usage of this particular tool, especially in a collaborative environment. So let me just move a little bit the window here. Materials data digitalization. If we take a little bit of a step back and think about the environment of creating materials data or characterization data, there's availability of data at multiple levels and everywhere. So this is a little bit what I'm trying to emphasize here on this slide. If we think about any standard characterization techniques or testing techniques, here I'm talking about a tensile test of a sample. There's typically different types of data that is created. There's, of course, the initial raw results data that contains number of points, the quality, its size, etc. This results data is typically used to be transformed into a property, a value. That's what we call here extracted data. In a tensile test, that would be calculating the Young-Pitch modulus, the yield strengths, work hardening coefficients, and so on. And it's typically linked to associated data, so additional information relating to the sample that has been used, which can be the sample composition, the microscopical picture of the interface at a break, grain size, we're talking about crystallized materials, and so on. Typically, when we create and we run a characterization or a test on samples, it usually goes within the framework of a research project where we try to compare new materials or evolution of existing materials to reference. So that's where all the related data comes in, either internal reference papers or publicly published research papers, technical reports, and so on. There's also a whole pan of data that is called metadata, that is linked to the experiment. So the data of the experiment, who has run the experiment, with which method, what was the environmental conditions, and so on. And finally, all of this data typically helps to feed in extended data sets, or in other terms, data that will be used for to consolidate the characterization of categories of materials. So that is data that looks into statistics, properties, statistical properties, modeling, analytics, and so on. And not only data is everywhere here, but it's also available in multiple formats. And the increasing complexity of data format also allows an increasing value that can be extracted from it. If I start by talking about 1D data, one-dimensional data, which would be properties of one data sheet, for example, or one property chart, such as shown here. Then if we think about what is available as two-dimensional data, that can be a combination of two properties about materials, such as HB plots shown here. But it can also consist in functional data, data evolution against time or temperature, or even statistical distribution of a property, which also give more insights on what the material really is. It's not just one point of property, but it's a distribution that can be linked to some understanding of the at the microscopic scale, for example. And then there's three-dimensional data or other type that also exists, and there's more complex things like a sample mapping versus a certain type of property or composition, two-dimensional data sets that are dynamics, such as shown here in this dynamic map, or other types of images, microstructural map, mix of data, or even sound that can be associated with materials data. So this shows that the growing complexity and levels of data available also enables different increasing levels of insights and value of data that can be extracted. The question is how typically this type of information is being looked at when you think about research labs. There's quite commonly two typical materials data journey in a research environment, which both starts by the level of data collection or capitalization. And that can be either capitalization of literature review, scientific literature review, but also combining together experimental or simulation outcomes that are being run. And this would typically be digitalized to have access to some form of database. Then from there, there's the next step is actually to look at leveraging the data, trying to understand some concepts or some fundamental science behind, and that can be done through visualization or selection of material, or looking into optimization and calibration of different composition and properties that we are exploring. But typically the purpose is to fulfill two major types of research profiles. One is to work on materials and process development, and the other is to work at product design or redesign. So if we look a little bit about these two types of scenarios, an example of material process design strategy is the following one. It's quite common that the starting point is actually to identify some sort of motivation. Now, a nice way to actually do that is typically to look at the property space of the most commonly available materials and to try to identify where there exist holes. And by holes, we mean spaces on the charts that would have an interest to be populated by new materials or improved materials, given that it would enable a better performance compared to existing materials. So in this particular example that I'm using to illustrate this, on the left here, I'm plotting Young's modulus versus density for the main families of materials. And the dotted lines that have been added here represents the contours of a performance index of a panel in bending. In other words, if we gradually shift this line here towards the upper left of the chart, emphasizing that here we're looking at a chart that is on the log scale. So if we shift this towards the upper left, we are gradually improving the performance index of materials that are within the line, and meaning that if we find a way to actually create materials that will fill in this empty space, it will most likely outperform every material given that application. So this way to identify the motivation of research is clearly easily done with either Granta EduPack and Granta Selector, which we mentioned a bit earlier. And once you've identified the motivation, you can actually look into how to fill in the holes that are mentioned here. That can be either through trial and error experimentation, which is the most classic approach, but it can also be in a different approach, which is through analytical modeling, ab initio, multiscale, and numerical simulations. And the most common practice nowadays is actually to try to find a way to combine those aspects, experimental and modeling, in terms of exploring the property space. And I was mentioning the creation of these property maps. So one of the things we work in the Ansys Granta space is a software called Granta Selector, which combines a library or encyclopedia, if you will, of different sets of reference data. And here, where it helps in terms of identifying motivation for research, is that it provides a good ground base for existing materials, but also it allows to do a bit of analytical combination of material on things such as the rule of mixture for composites, analytical model for hybrids, materials, multi-layers, and so on, which basically would enable to see the potential of combining existing grader materials into new structure, new format of materials, and see how they would outperform the material property space. And by doing that, you can start to communicate and argue on the potential and the direction that different research projects should be going into. So that was about the material and process development approach. Another approach that was mentioned earlier was a more product design strategy approach into materials research. And here the intent is to combine on one end optimal material and selection process, and on the other end optimal design. So a commonly spread methodology to do material selection or process selection is the Ashby methodology, which is summarized here, and basically consists in applying in restricting the data in excluding candidates within data sets that do not fulfill some set of requirements, and try to rank the remaining candidates. These top candidates would typically be used to go on the next stage, where you look at the optimal design, and that's where you would use the material candidates for finite element analysis setups in order to benchmark the materials and find optimal design. The intent behind is there again to evaluate the trade-off between the different sort of objectives that are fixed within the project's description. And it's quite common that this is actually not really a linear process. It's something that is done on multiple loops, because it's quite common that once you start to reach the stage of optimal design thinking, you reassess a bit the initial characteristics and requirements you had on your material. So this approach is quite simple and robust method, and more spread. There do exist a few more advanced product design strategies when it comes to materials research. one that I'm mentioning here on the left is simulation-driven design. And to keep things short, it consists of taking into account the fact that in the vast majority of cases, 80% of the costs of the future costs of product development are embedded in the initial design stage. And by finding a way to do what is scenario at a simulation scale, or if you will, deploying some level of virtual prototyping much earlier than the way simulation is used nowadays, if you're able to achieve that, you actually make a lot of progress in terms of time and cost savings compared to traditional design. Another approach to advanced design strategy is integrated computational materials engineering, or ICME. And this is trying to have an approach where you look into process, structures, properties, performance, and multi-scale interaction, where basically at each level of scale of product development, you both have an approach of experimental and modeling that talks to one another within the same scale, but also with the different levels of scale. So given these different types of research materials, I've said a bit some of the landscape here, but that leads us to the question when it comes to research, who uses these different types of strategies and how they work together to actually embed that. So in this next slide, I'm trying to paint a little bit the picture of what could look like the landscape of stakeholders in a research project. And by research project, I mean that can be PhD thesis, research lab teams, collaborative projects, or industrial partnerships. In these cases, there are typically PhD or postdoc students who are the most active in terms of running some of the experiments or simulations. And it's not always the case that they are familiar or have the best practice in terms of doing capitalization of their data. Now, they would typically be discussing a lot with their direct supervisors, who for that person typically would like to have easily access to analyzing the tons of data that their direct students are generating to look in depth some of the analysis that can be done. Most research are also nowadays connected to a more modeling or numerical plan of a project. So most likely within the same research group, there will be a numerical modeling expert involved. And for him, the interest in terms of material data access is to know which materials inputs he should be using for the simulations and what are the models that have been confirmed by experiments. And finally, there can be some external partners for whom the interest is to have access to the homogenized data from their academic partners. And within this landscape, on top of that, the amount of data becomes huge when you think about research projects in any field of science. You can think about metallurgy, which is a more classic field of science. But if you think of things like healthcare or sustainable developments, these are topics where an intensive multidisciplinary component is part of it, meaning that it increases the number of people that collaborates within one another on the topic. So there's definitely also a need behind to making the shared data accessible with traceability of how it interlinks with the different experiment sets that have been carried out and the initial material it comes from. And there's also the need to create bridges between different scales and different physics that use these different tools. So there's an interoperability component that is important here. So the solution to actually try to address this is to have a data-driven science, engineering, and materials informatics approach. And by that, I mean the field of study that applies the principles of informatics to material science and engineering, in the intent to improve the understanding, the use, the selection, the development, and the discovery of materials. And this is very simply schematized here, but it's not just a trend, it's really the future of material science in terms of helping helping in the understanding of some of the behaviors of existing and new materials. Now, when we talk about digitalization of the materials research space, if we think about other sectors and how they've become to transform from a digital standpoint, there's many areas which are already quite ahead. If we think about product design or CAD, finance, human resource, these are sectors that are already quite well transformed from a digital standpoint. Materials up to now had tended to be a bit behind. There's a few reasons for that, some of them being the fact that it's a technically complex domain that puts together multiple aspects of fundamental science, which requires highly technical skills to put in a and use wisely in a digital format. When it comes to the industry side, materials are things that are typically owned across multiple departments. So that doesn't help into having a standardized way of thinking about materials properties and how we store information. And still on the industry side, materials department would tend to be seen as a cost center rather than an area where an industry could invest to gain some time or to develop innovation. Now, all of this has been changing. There's the global digital transformation trends that really influences this. But there's also the factor that there's an explosion of data available. And that also applies to materials research. If we think about the type of outputs that our current characterization or testing equipment generates compared to 15 or even 10 years ago, the amount of data that is now at hand is huge. And it's not always the best practice on how to use that is not there yet. Another reason for this change happening is that some strategic material sectors do need digital transformation to actually really burst. If we think of additive manufacturing, for example, this is an area where having this digital transformation approach is crucial for its development. Now, still relating all of this to research projects, this component of digitalization is more and more looked into. And when we have a look into the current EU-funded research calls that exist, they now all tend to require that the project has a plan to fulfill the FAIR digital assets principles. So FAIR is for findability, accessibility, interoperability, and reusability requirements. So that leads me to talking about the Ansys Granta platform that we developed in the intent to help data-driven science and engineering. If I go back to the picture I was describing a little bit earlier, what we're really trying to address here is to put a central common tool or platform, if you will, and this is our Granta MI software, the center space of research projects. And it should not be seen only as a data platform. It is also something that gives access to the materials informatics that I was referring to a bit earlier. Now, trying to explain where this platform fits in the ecosystem of Ansys. So for those who are not fully familiar with Ansys, Ansys is an American software company that developed multi-physics software. I'm showing here some of the main core physics that we have software packaged to do simulation on. And these, in these areas, we typically link the outputs of these simulations to simulation and automation and optimization platforms on one end, but also running these simulations also require having access to materials information management, because if you think about it, every starting point of simulating these different types of physics requires an input in terms of materials modeling. And that's where the Granta MI platforms comes in. It is a very unique space where you can have the simulation require some inputs in terms of materials properties, but also this is a space where the outputs of the simulations can be embedded and captured. So from a practical side, what are we talking about when I talk about Ansys Granta MI? So as opposed to Granta Selector EduPack that I was mentioning earlier, which is a local software with databases that are fixed, the Granta MI platform is a server-based software. So it's based on the SQL technology for those who are familiar with it. And it is something that is accessible to users in the web browser interface. What will be populating the system? Well, it can be, of course, all the proprietary information from the organization where it's being used. That can be both legacy historical data that could be at this stage spread out everywhere in different formats. And we have way to actually import all this legacy data into a centralized way, but it can also be fitted in by connecting the platform to existing characterization techniques and testing machines with automated import. There's a possibility to also have access in the database to external libraries of reference data, and that is really depending on the applications. From there, on the user side, there's different things that can be, that there's different ways the data stored can be used. It can be through just simple web platform service for additional analysis and visualization tool, but it can be also to export some of the data into simulation packages on one end or into running some scripting routines. Some of the core requirements behind the way we've constructed the Granta MI platform is to ensure that the tools that are being provided allows a full materials data lifecycle traceability, access control, and control of the workflow that are being implemented. And the third and most important bit is the specialist materials data structure, which is this central bit here. In other terms, it's the way the data has been organized. Now, at Ansys Granta, we've had the know-how in terms of organizing data for the last 20 years, and we've embedded that by creating different sort of schema or data organization templates that are provided alongside the Granta MI platform. And the rationale behind is to provide a data structure that will enable to capture complex data, but also their interrelationships. And that is actually done by making sure there is at every stage this interlinkage and traceability. So if I think about a project or different projects that an organization might be going through, which could be organized into different test series. From there, I can quickly look into what are the different test data that have been run on samples. If I take the example of tensile tests, and from there I can quickly identify the samples that have been tested. Where do they come from? What is the full material pedigree? What is the equipment that has been done? But also the outputs of the test, how they have been used further along the line in terms of generating statistical data or materials modeling for simulation. There's the possibility to continue having the version control of all this database, because again, as I was saying earlier, this is a server-based live database which people can be entitled to change in a direct way. And you can also define who should be accessing which part of the database behind. Now, making the link with the wood-based materials or fiber-based materials and talking about composites. Now, of course, when we think about organizing the structure of a database for composites, this is particularly challenging compared to other family groups, and that is for a few reasons proper to composites. First, there is the complex pedigree information, because composites are, the combination of a matrix, a reinforcements, a way those matrix and reinforcements have been organized. That means the structure, the layup, the orientation, and even the conditioning. Composites also requires some specialist types of testing and data. For example, adhesive bond strength or fiber toe counts. These are types of properties that are unique to this material subset. There's also the anisotropy component of composites, properties varying in different directions. And there's finally the dependence of the properties on process history and parts geometry. So here the question is how to describe material data and how to represent those multidimensional data. And that's where having a good expertise and understanding of how your data structures should look like is important. In the Ansys Granta MI platform, we do have a dedicated schema or database structure, if you will, that do reflect the specificity of composite materials. So if I now continue explaining a bit on how the platform is used from a digitalization standpoint, if you think about different testing or equipment machines, here in the example of additive manufacturing, this will generate typically different formats of raw data that can be text, CSV, PDF, images, and so on. And the Granta MI platform allows to automatically configure the machine output to be embedded in the right format in the database and quickly have access to the correct values and format. What I'm showing here, continuing on this example, is a few screenshots of a material record that a user would be accessing on the web interface. We see that there's different properties that are in the materials record. Sorry, here we also have a bit of fatigue information and curves. It can be different curves, types of data, such as stress strain here, for example, or we could think of creep or temperature dependent properties in that example. But it can also include other types of information about material, things like images of the samples and additional analysis that we might have been doing with different techniques. Another important use to emphasize a tool to emphasize when it comes to the platform is the fact that it allows things like Python, MATLAB, or R inquiries to come in and take some part of the database or the properties to run in-house tools. And that is quite handy if you need to do advanced calculations or modeling tools based on existing routines you might have already created. And then because the platform allows this, is open for such scripts to make inquiries, it allows to have automated way of in exporting data, running some calculations, and importing it back with traceability there again of what has been applied to the data. On the Python side of things, there exists now on GitHub a Ansys group where such sort of scripting tools are being made available as the community starts using them. Now to conclude the presentation, now I'll finish the last part here by talking a little bit about industry and research usage, emphasizing a little bit more the collaborative environment component here. On the industry side, I will not extend too much on this type of application. What I'm showing this on this slide here is just a sort of overview of some of our industrial customers. And the point is the point that I'm looking to make here is that there's quite a few sectors in which this approach of materials data information is being used. If we think about aerospace and defense, things like energy sector, or even the healthcare product space, those are areas where we have industry using this type of platform. Now, when it comes to a research example, I'm going to try to illustrate this in a few ways. The first way to do this is actually to talk about some research outcome that a colleague has done. So one of my colleagues used to work, my colleague, which is David Meshier, used to work in a research institute in Belgium, where one of their projects was to look into indentation and multiscale characterization of titanium alloys. The need behind at the time, their approach was to do these different steps in the research project: multiscale characterization, collecting EBSD data of some samples, multiscale statistical analytical calculation, comparing experimental results to existing codes, and trying to model and anticipate crystal plasticity based on the combination of the former. This was all done in sequence before and stored in different ways. Now, there was clearly the value here of creating a materials properties database and a simpler modular workflow using Granta MI platform in the intent to do optimization, parameterization, and optimization of this calculation and modeling outcomes. So what I'm showing here is the schema that has been created specifically for the project. Here you don't need to look at the details. I'll emphasize a few points. The first one is that all rectangles in yellow represent things that are measured data tables. And we have here on the top measured data tables of sample scale characterization, and on the bottom at the crystal scale characterization. Both of these groups here are linked to the material sample or the different crystals that have been identified from a sample to do the crystal scale characterization. On the outside, there is also links to calculated data table. So on the crystal modeling scale here, or on the sample modeling scale here. So the message here is to illustrate that it's an example here, but it shows that it can be user defined and organized in the intent of addressing the specific research project goals. So talking a little bit more about what was actually done in this case, there was a full set of data acquisition that was being done on a regular basis. The Granta MI platform allowed to embed an automated pre-processing of the raw data routine, which would automatically import in the already correct formats the experimental measurements in the database. So putting all of this together in a workflow, the platform enabled to have this database with a standardized ways of importing data from which one could easily start doing some different levels of exports of the data. First export routine would be to do a bit of analytical modeling with external software and feeding it back the outcomes into the Granta MI platform. The next step would be then to look at crystal scale modeling and understanding how the simulation of those crystals and the information that was captured would fit the experimental results. And that's where a set of optimization could be coming in to actually continue to have the traceability in the MI platform, to have the continuity of the MI platform of the progress made. And then towards the end, the sample scale modeling would be able to be run, populated by the crystal scale modeling result outputs. And the outputs and what had been enabled by implementing this database practice and also workflow schema is regrouped here on the modeling and optimization at the crystal and sample scale. So that was more on a specific research project example. We've also been involved quite a lot in collaborative research project or networks. Here, this slide shows some of the consortiums of projects that we've been involved with. So we have here on the left a few networks that we are part in. We've been running some consortium with NanoHub and NASA for over 15 plus years on data management as a whole. And we've been part of many European funded projects in which we were helping in the different outcomes of project by taking care of the digitalization part of the research projects. That includes, for example, composelector project, which was on composite design, but also things related to metallurgy as the accelerated metallurgy project. So that's actually one example that I will slightly extend just to give you some sort of insight of the things we contribute to in these types of projects. Accelerated metallurgy, in a nutshell, the goal of this project was to accelerate the design of new alloys, and the approach taken to do that was to combine high through output simulations, high through output synthesis, and high through output characterization. And you can clearly understand by how high through output this meant an intensive generation of data at each level. So the Granta MI platform contribution was to actually provide the relevant database structure to manage these tens of thousands of both simulations results on one end, and then from there enable the search and selection of the most promising alloy composition. Because the rationale behind was to sort of scan combination of up to 9 elements in one go and see what sort of properties you could, from a modeling or simulation perspective, expect. And out of that, quickly narrow down the candidates that we should push at the sample generation synthesis. And I'll finish by mentioning a more recent project that is now on the go, which started in 2021. This is an INPRESSME project, and it has the specificity to look into bio-based material in an open testbed approach. And some of the main goals behind is, one, to look at developing market-ready products from bio-based materials, and two, to support the digital transformation by providing all the data and life cycle value chain modeling tools as part of the materials that are being explored. So, of course, here, when it comes to the Granta MI platform and our involvement as Ansys in this project, we are contributing mostly to the second part of this objective, where we are creating the relevant platform to actually fulfill the value chain modeling tools goal. So that comes to an end of the presentation I had shared today. I had prepared today, and before coming to the question and answers, I'm summarizing here a little bit some of the things we covered. Organizing data, having a traceable and in a traceable way, and then having it available and in an interconnected way. This is something that really contributes to building knowledge over time and is strongly relevant to the advancements of material science knowledge. And it does that in multiple ways. One can be the speed and consistency in the data processing that is being generated, but it also being done by making sure the relevant information is shared in a collaborative way. And it also gives the opportunity to have better insights of material science complexity by establishing those relations I was mentioning. So having this approach is an increasing component of research best practice. I mentioned the requirements about the FAIR principles earlier, and that's one of the things the Ansys Granta MI platforms contributes to. After this session or later, I'm very happy to connect explore how to get a project started or to test this approach if you feel that it's actually would clearly connect to the way that some of the research is being addressed in your respective groups. So thanks again for your time, and I'm happy to try to answer some of the questions now.
Dear Nicholas, thank you so much. Really nice to hear about the Ansys Granta selector again. It's not the first time I listen to the presentation, and I can see there is a question from Rohan. So Rohan, I allow you to speak. So if you wish, you can maybe just unmute and ask your question.
Can you hear me?
Yes, very well.
Yes.
Yeah. Thank you, Nicholas, for a wonderful presentation. And this is the first time I'm hearing about the software, so it's truly magnificent what the software can do. This was something missing, I suppose. Then my question is more on the fundamental side. I just wanted to know, how is the database updated in the system? So is it only the user base, like we found some different kind of results and we update in the software ourselves, or is it also updated by the company?
Oh, yeah. Okay. So good question. So two things that I mentioned. So one is that the Granta MI and the database and the server is, well, we encourage it to be owned by the institution. So we would not be hosting the data because it's your proprietary of it. So that's one thing. And the server itself, you can configure as you wish. So you can define people that have admin roles, people that have editors roles, and people that have just read mode roles. So you can actually configure what you allow. And then from there, the users can either import manually records directly from the interface, or if it's for large scale sets of data, then the best way is to use there's automated imports that exists, or that can be configured if it's not fit to the machine that you're using.
Thank you. But then I have a follow-up question.
Sure, yeah, go ahead.
Then if this is the case, then do we get a reference to the data where we are getting from? So for example, I try to use a data from system for some XYZ material, and I want to know where that data came from. The particular research article, can I get an access to it? Or do I know like which article it's coming from?
Okay. So I think I see the question. So there's two things behind. If I go back to this slide, this one, no, the one before. There you go. So when we set up a Granta MI platform within the research lab, by default it's empty. In terms of the data structure is here, but it's empty by default. But you can eventually also require to have access to reference data libraries. So this is something that we at Ansys work on, that is available in Granta MI, but also in Granta EduPack and Granta Selector. It's a set of reference data. Those are typically have links for the reference. Now, as a research lab, you might be doing some research on very specific fields that we don't have reference data for, because the vast majority of our reference database are more on industry engineering standard material. So on the research front, it's depending on the case, it might not be fully useful. What happens is some research lab is they actually, as part of the implementation of Granta MI project, they also take the opportunity to capitalize all the literature reviews that PhD students or different groups might have been done already in the past, but have this common way of putting together all the properties of research that exist. And when you do that, you can actually configure to make sure that if you have some properties of material, you can link it to the corresponding paper and reference. So you can basically tailor and decide what level of information you put in the system.
Okay. So simply put, if I have to cite one particular comparison, let's say my experimental results from the historical data, do I cite the Ansys database or do I cite the original paper?
Okay. Okay. So I guess that's another question. Then, so if you use some of the Granta Selector or Granta EduPack, if you use some of the charts, then you cite the software.
Okay.
Yeah. If you use some of the software, you cite the software. Yeah.
Yeah. Okay. Thank you.
Rohan, do you have any more questions?
No, I'm done. Thanks.
No? Great. Rohan is actually a researcher in the same team where I also work. He is now doing his PhD studies. So I will encourage Rohan to look deeper into the software package that we have. And if I remember correctly from the previous presentations, there is quite a large database on the existing materials properties, right, Nicholas?
Yes. So I think one important thing to emphasize, the vast majority of the things I've talked about today is the Granta MI platform, which again is a live database that can be configured, which is separate from Granta Selector, which also have something we developed. But the particularity of Granta Selector is that it's a fixed, localized software, while the Granta MI is a platform that is because it's on a server, it can be accessed and changed at the same time by multiple people in groups. Now, in both cases, we can make available some different sets of materials data. I can actually just, if I look up here.
Because basically what I understood, the value of the software that we have, for instance, at Fiber and Polymer Technology Department at KTH, that we have access both to the existing databases, but we can also create our own databases and then plot them all in the HB plots form, for instance, and make our own material properties databases.
Yeah, exactly. So you had understood correctly. So I'm sharing now the screen of the Granta Selector software, which, okay, let me open one of the databases.
Because for the databases, you have different packages depending on what kind of material types, properties you need to access. So you can select which you want to look at.
Yeah, exactly. So there's quite a few databases that are available, things that relates to additive manufacturing, for example, to composites or coatings, materials, or even eco-friendly properties of environmental indicators. In each of these cases, the data can be accessed in a similar way, and so basically each of these topics are data tables which have their own specific structures, given that they address a particular material group or topic, and then from there, that's where you can access different sets of properties. Now, within Selector, you can indeed either duplicate record or add records and so on. However, this is a localized interface. It's a localized software. It's not a server-based software. So there's quickly a limitation whenever you look more into doing collaboratively some research where there's multiple stakeholders that change things at the same time. It doesn't mean that there's no value behind. What I'm just saying is it's for different usage. Here, the selector would maybe a bit more for maybe benchmarking or small project of adding data. While if you wanted to do at a larger scale, where there's multiple stakeholders and there's this need for live database behind, then that's where the Granta MI platform is offhand.
Yes. And I think that's very valuable because we are creating the new materials. So we can create our own databases and then create our own material universe that we can try to compare to and see if they fill those holes that you presented in the Ashby plots. That would be very valuable, and that's what we were doing. Really good. Are there any more questions? No? Then with this, I would like to thank Nicholas and thank to all participants and also to Christine, who is helping me to co-organize this webinar. And at this occasion, I would like to also use this opportunity and to invite you all to the upcoming conference that we are organizing with the Treeserach and Treeserach Research Infrastructure. So it will be a Treeserach Insight conference that will take place on the 24th and 25th of May in Lund. And at the conference, we will deeply focus on the advanced materials characterization and processing. There will be scientific presentations, possibilities for networking, both for industry and academia. And the last but not least, we will have two important study visits to the facilities at Lund University of Technology and also to the MAX 4 facilities. So we will even see the brand new beam line called 4MAX for the analysis of materials from trees. And we will also continue with more webinars, so stay tuned. This presentation will be available on YouTube, so please share it also with your colleagues. And if you have any questions, please feel free to email us directly, or you can get in contact with Nicholas also directly using his email. Thank you so much, everyone.